Unmanned area vehicles, or UAVs, continue to play an increasing role in homeland security, military operations, and civilian sector applications. Used primarily for surveillance and target acquisition, these vehicles have significant mobility advantages. With the exception of UAVs with weapons payloads, the vast majority typically try to avoid contact with the ground rather than interact with it. The aim of this research is to develop a mobile manipulating unmanned area vehicle, or MMUAV, that goes beyond simple pick and place. This artist's conception shows a futuristic area vehicle with multiple dexterous arms. A prototype vehicle was constructed using an off-the-shelf quadrotor. These types of rotorcraft are simple, have strong hover control, and good payload-to-weight ratios. The drawback of the quadrotor is a tendency to drift due to the inherent instability of the rotorcraft from its motors and rotors. To compensate for variations in roll and pitch during flight and manipulation, a buoyancy envelope was attached to the quadrotor to provide restoring forces and an increased moment of inertia for the vehicle. By analyzing test runs with and without the buoyancy envelope, we have verified that the hybrid structure does improve flight stability. Experiments show that the prototype vehicle is capable of both flight and actuation. The prototype proved to be very difficult to control manually, even with the buoyancy envelope. In this test scenario, human operators are controlling both the quadrotor and manipulator arms. With the arms fully extended, the aircraft instability prevents object manipulation. Therefore, we implemented computer-aided control using a motion capture system. The vehicle is seen here interacting with a target object with all three manipulator arms. A closed-loop controller compensates for disturbances caused by changing centers of gravity during arm actuation and contact with the target. The importance of these experiments is to characterize the forces and torques generated from both arm articulation and reaction forces during target manipulation. Initial results are promising, and the prototype vehicle has proven to be an important milestone for current and future work. From the lessons learned of our prototype vehicle, we have also built a miniature gantry test rig to emulate the pose of the UAV and perform mobile manipulation in a controllable and repeatable manner. Based on Drexel's Systems Integrated Sensors Test Rig, or SISTER, the flight emulator uses model reference adaptive control to eliminate error between the gantry state and the flight dynamics model of the aircraft. Due to the difficulties of using multiple manipulators and end effectors on an aircraft, a hybrid impedance control strategy was implemented. The use of force feedback and impedance control is a well-practiced approach for manipulation and provides an interesting advantage for the aerial manipulation problem. The sensed forces can be communicated to the rotorcraft stability controller to provide overall stability. Future work will include larger and more dexterous manipulators with an aerial platform capable of greater payloads.